Now welcome back to my channel, Aspen Plus made easy for chemical engineers by Abass-Giwa Muhammed today. In today's video, we shall look at the fundamental relation for the velocity of liquid flowing out of a tank through an orifice. So in a later video, I may connect this theory to process simulation. So regarding the milk water discharge, my justification before a jury in response to Sir Steve Leisure is review on Lickdale posted by Ibrahim Yunus Muhammad. This was my response on the platform. Both tanks are emptied at the same time, and this is the explanation. So let's consider the flow, that is the amount or the flow out of the system. And what is the system? The both tanks. So is V is equal to root 2GH. This V denotes the exit velocity, G denotes the acceleration to gravity, while the H denotes the head. And what is the head? It is the distance between the orifice and the maximum water level or maximum milk level before the orifice is opened. So the height between the orifice to the water level is known as the head. This relation, that is V is equal to root 2GH, is used to calculate the flow rate of fluid moving out of a system. It is known as Torricelli's equation. It was reported to be derived by Evangelista Torricelli in 1643. That is, I think, Italy. Yes. That means the amount of fluid moving out of the tank now is V1 is equal to root 2GH1. And the amount of fluid moving out of the milk tank is V2 is equal to root 2GH2. Now the funny thing now is that GH1 is also equal to H2, that is the head, the level between the orifice and the water, and the height between the orifice and milk level are the same. So that is the meaning of the fact that the parameters remain the same, that is no density proportionality. Why do I say no density proportionality? Yes, if there is density in the relation, that means there will be variance, that is the density of water is not equal to the density of milk. In that case, the flow, the exit velocity will have a different values. There will be different values for the exit velocity for the water and the exit velocity for the milk. So in that case, we may say one liquid may be drained out of the tank faster than the other. Since we have V is equal to 2GH and they both have the same head and acceleration due to gravity is constant, so therefore, they will be both drained at the same time. Second fact is that considering the Reynolds to determine the nature of the fluid. Reynolds number helps to know the nature of fluid. In engineering, when the Reynolds is less than 2100, is known to be nominal. Why it is, if it is between 2100 to 4000 something, so it is transitional, and if it is more than 4000, that means it is turbulent. No, Reynolds helps to know the flow, the nature of the flow of the fluid. Now, considering this problem now, but we have a problem here. The problem is that the Reynolds is now fighting or is now going against a bigger force. And what's the bigger force? I will explain this in this video. Sir Steve Leisure reviewed and said, can you apply some numbers and do an example to prove to a jury? Yes, sir. Of course, it's possible, but applying some numbers would not be credible as much as applying a simple practical or providing an illustration. And that is what I'm to do now. Here is the problem. Two bowls of equal volume are 1/3 filled with water and milk with an open orifice of the same area. So if the water and milk level in the tank are the same, which tank is emptied at the quicker rate? And my response was both tanks are discharged, emptied at the same rate. Please don't forget to like, subscribe, and watch +1 Model 3 from the playlist on my channel. which was all about Aspen Plus simulation of non-conventional components. We have a good assumption to make. Here the assumptions will be stated here. First of all, we have to understand that the state of the system should be steady, and the system should be an open system. Why? The open system, it is open system because there is an exchange of mass between the environment and the system. And what is that? The liquid moving out of the tank. And the system is the water tank or the milk tank. The assumptions are the orifice, that is the outlet of both the tanks, have the same diameters. Even though it was not explicitly stated in the image, it is an implicit factor to consider. Then two, the two tanks are placed on the same height above a ground level. As it is seen on the image, both are on the same height. However, some people, especially engineers, might not accept the fact unless a dimension is drawn to specify the equity. Then 3. No reaction takes place within the system. 4. The nature of the fluid flow remains the same for the two tanks. That is, nominal flow preferably. That is, the orifice may change the flow pattern in such a way that the milk may be linear while the water goes turbulence at a particular point. So we assume that the nature of the fluid flow remains the same. Then 5, the milk solution is homogeneous. Yes, of course. We assume no form of condensed milk remains within this tank, especially in the milk tank. So because sometimes it may be heterogeneous. So in as much as the milk is in liquid form throughout, so fine. Then 6, the orifices have smooth surfaces. Yes, because the orifice determines a lot regarding the pattern of the flow. Hence, it is taken as a factor to calculate the discharge coefficients. If the orifice of the milk tank has surface, while the orifice of the water tank has a smooth surface, so therefore the flow will be different. The amount of fluid that comes out of the tank will vary in that aspect. The variables, to make my attempt more explanatory and concise, the following variables would be declared in terms of the appropriate symbols and letters. VW, that's the volume of the water, and that's the dimension L3, and H1 is the height of the water level in the tank A, as labeled in the image as well, and that is the dimension is L, and H2 is the height of the milk level in the tank B, that is the dimension is L as well, and MW should be the mass of the water, and the dimension is M. M should be mass of the milk, the dimension is M. Rho W, the density of the water, dimension necessary, and density of the milk as well. F, force of attraction, and we have G, gravitational constant. Others are ME, mass of the heart, the MACC, mass of accumulated, ME, mass into the tank, and dimension is M as well. So A1, that's the area of the water tank, dimension is L. A2, area of the milk tank, area, yes, the surface area of the milk tank, and A0 is the area of the orifice, the surface area of the orifice, and H0 is height of the orifice. Now let's go to physics. To a jury, this is the particular problem, right? Let's start from physics. Place a big ball and a small ball on a small height above a ground level. Then push these two balls at the same time until they fall onto the ground. What do you discover? You will discover that both balls fall, reaching the ground at the same time. Regardless of their mass, they both comply with a major force of gravity, and that's the bigger force. Yes, of course, this is proven by a force of gravitational force law that states that the force of attraction between two masses is directly proportional to the product of the two masses and inversely proportional to the square of the residues, that is the distance between them. And I will use this one to justify my claim regarding the flow of the fluid out of the tank. Why do the two balls fall onto the ground at the same time? The heart drags the two balls towards its center by a force that causes a steady acceleration. And what's the steady acceleration? G. The force does not care if you are bigger than anyone else at its own divide rate, which is always between 9 to 10 meters per second square, depending on the location. Let's see this as a car. A small ball, a tire were tied around the car. If the car starts, do you think these objects tied to the car would move at their own speed, or will move at a different acceleration? No, of course. They will always move at what? At the velocity or at the acceleration of the car, unless the objects tied to the car have higher masses than the car itself. Now, let's consider this. The heart itself has the biggest weight compared to these masses, that is the two stones. So when it drags them at a particular acceleration, and which is what? Between 9.0 meter per second square to 10.0 meter per second square. From this equation, F is equal to G m1 m2 over r squared, where m1 is the mass of the heart and m2 is the mass of the object and r squared is the distance between them. Then gm1 over r2 is equivalent to the acceleration due to gravity. In that case, we substitute g for gm1 over r squared, and that gives us F is equal to ma, that is gm, which is ma. Are we getting that? So the force of gravity now is now equal to the mass of the object and the acceleration due to gravity, and that is a. In that case, let's consider the water tank and the milk tank. The force accumulated in the tank, I believe, should be equal to what? The force going into the tank minus the force moving out of the tank, right? From restoration of force and taking the momentum balance. Agreed, right? Now, the force accumulated in the tank is equal to the force in that is pushing the water and the milk within the tank. And what's the force? It's force of gravity. Force of gravity, of course. It is pulling, dragging them towards its own center. And the force moving out of the tank will be the force around the orifice. The force around the orifice is being controlled by the force of gravity. From this relation, I derived a relation that helps us to know the amount of fluid that leaves the tank, the water tank and the milk tank. Therefore, the force moving the mass of the water and the milk does not regard the difference in their density or the difference in the masses. It doesn't care. You must follow its own defined and regulated speed or acceleration, and that is between 9.0 to 10.0 meter per second square. Therefore, the water and the milk run within 9 to 10 meter per second square, so they will be drained out of the tank at the same time. Let's assume the volumetric flow rate of the water in the tank at any time t is Fw naught, that is the flow of water coming out, and this is the equation I recently derived but not yet published, but I'm still working on it to gather some facts and literature to support my derivation. But this aside, I'm not going to use this, but this is the relation and the volumetric flow rate for the water, the volumetric flow rate of the water in the tank at any time t is also this. So we are going to apply Torricelli's equation, which is the flow rate of the fluid out of the water tank is equal to the flow rate of the fluid out of the milk tank, which is equal to what? A naught delta t, the square root of 2gh. Now that it had been concluded that both tanks will be discharged at the same time, now let's calculate flow rate out of the tanks. Now I'm not going to use this relation for now. I'm going to apply Torricelli's equation. Let's assume that the following data is given to describe the situation. That is, Vm, volume of water in the tank, is 50 liters. That is 0.05 meter cube. And the head, the water level in the tank, the water height, and is equal to the milk height, and that is 0.5 meters. Then the head, that is the pressure head, which is the distance between the orifice and the water level or the milk level, and that is 0.45 meters. And the G is acceleration due to gravity. Let's take 9.80 meter per second square. Then we shall use the opportunity to calculate the flow out of the water and the milk tanks. Let's calculate the area of the opening, because from Torricelli's formula, it says that the flow out of the water tank and the flow out of the milk tank is equivalent to this relation. That is the area of the orifice 1 times the time changes times 2gh, while h is the head, the pressure head. Therefore, let's calculate the area, and the area, according to mathematicians, is pi r square, where r is equal to the half of the diameter. Because we are not being given the radius of the orifice, we will make use of the diameter in place of the radius. Radius is equal to diameter over 2, so we are going to substitute the values of d and pi. And the value of d is 0.2, which can be seen here. 0.2, which can be seen, that is the height of the orifice, which is the diameter as well. When we insert that, we will get this. We can confirm that on our calculator. So we get this. After that, then we move to calculating the flow rate out of the tanks. And the flow rate of the water out of the tank is equal to the flow rate of the milk out of the tank, which is equal to the area of the orifice, and which is this 0.00034 meters squares. At the time, we are working at the rate of 10 seconds. Let's assume what is the amount of fluid that will flow out of the tank within 10 seconds. So the time here is 10 seconds. If you want 60 seconds, that is 1 minute, we put 60 here. Then times the square root of 2, that is constant, it won't be changed. G, that is acceleration due to gravity, and that's 9.81. And the head is equal to 0.45, which was described here. The head is from the orifice here to the top, the highest level. And that should be measured before the orifice is opened. That should be, yes, it should be measured before the orifice is opened. And we will result to 0.0093 meter cube per second. 2 liters we divide by 1000, and that will give us 9.33 liters per seconds. And here I think the volume here is 50 meter, that is 50 liters. So for every seconds, so it will discharge 9.33 liters of water and the milk at the same time. Do you want me to simulate that using Aspen Plus? Like, share, and subscribe for more at Engineer AGM Plus.